So thanks for the introduction, and I'm very glad to share with you our research having the title "The Emergence of Latent Structures in Natural Language Processing." Sorry, and so this is the overview of today's talk. Firstly, I will give you an introduction or the background of our research. Then I will talk about two papers of ours. The first paper is about phrasal logical reasoning, and the second one is about unsupervised trunking. And finally, I will end with this talk with a discussion and the future directions. So this is the background for the end-to-end neural network. It is about the connectionism, which is a very popular school of AI. So end-to-end neural network aims to learn rich representations from data. However, it has some drawback. The learned representation is very difficult for our human to interpret. So that's why it makes the end-to-end neural network as a black box machinery. And this was a very popular or highly cited paper from the domain of machine reading comprehension. And you can see that they tried their best to build a model with great transparency by alleviating different kind of feature engineering and also adopting the attention mechanism. However, since the model is still operate in the continuous representation, so it is still hard for our human to interpret what is actually going on inside the model. So in other words, it is still a very big black box model. And in this talk, we are going to introduce a concept called symbolic bottleneck network. So for the symbolic bottleneck network, it is expected to output discrete and interpretable unit in some intermediate layers. And it is those interpretations unit is good to explain the reasoning of the input and output decision from the models. And since we have a bottleneck in our neural network or in our symbolic bottleneck network, we can still achieve comparable performance at the black box model. This is the findings from our experiment. So let's take a look at our first paper with the title Weakly Supervised Expandable Phrasal Reasoning with Neural Fuzzy Logic. It is a paper published in iClear just 2 years ago. So let me to give you an introduction of the task we are going to address in this study. It is called the natural language inference task. And it was a very good task to test the logical relationship, reasoning for a model. So, to be more specifically, it requires understanding it requires the model to understand the logical relationship between a sentence pair. So here I have an example. We have a premise. Two musicians are performing on stage with their instrument. And the other sentence, also called hypothesis, there's only one musician performing on stage. And the correct or the ground truth label of this sentence pair is contradiction. And in short, this is a three-way classification task, and we have the label among entailment, contradiction, or neutral. And deep learning models such as BERT, if you know BERT, it is an encoder-only transformer model that was portrayed on a large bunch of text data. And such BERT model can excel in NLI accuracy, but they lack transparent reasoning because for a predict NLI labels, for example, contradiction, we don't have any idea why such label is getting predicted. So the motivation of this study is we want to provide explicit phrase level explanation for the NLI decisions. And we propose a framework called explainable phrasal reasoning, or in short, EPR. Our EPR is expected to output the phrasal level reasoning besides the sentence level prediction. So let's take the previous example for a premise, three musicians are performing on stage with their instrument, and a hypothesis, there's only one musician performing on stage. So our EPR model is expected to not only to provide a sentence level prediction, which is contradiction, but also to provide a phrase level reasoning of why the contradiction label is getting predicted. It is because in a phrase level reasoning, three musicians should be contradictory to one musician, and are performing on stage should be entirely performing on stage. However, but leaving the with their instrument on a line, which does not contribute to the reasoning. And our EPR framework follow a three-step process. For step one, we detect and align phrases. And for step two, we predict phrasal relationships from those aligned phrases. And for the step three, we induce a sentence level decision using fuzzy logic from those predicted phrasal relationships. And for the step 1.1 of phrase detection, we do an extraction from of content phrase from the raw sentences. And those content phrase might be prepositional phrase, noun phrase, or verb phrase. For the other phrases we are not handled in this study, we treat them as the individual phrases if they are open class words. And those extraction are based on the handcrafted rules by utilizing some open source linguistic tool like NLTK or Spacy. So now you know that we are doing in the phrase level reasoning, and I think it is worth to mentioning that the reason why we think the phrase level reasoning is better than word level reasoning is because a phrase can often provide better context as a reasoning unit. And this is also supported by our analysis. And for step 1.2, phrase alignment, we encode for those extracted phrase, we encode each phrase with local and global embeddings. So for the local, it means that we just send each individual phrase into an encoder model and get the embeddings. But for the local, for the global embeddings, we just instead send the entire sentence into the embedding model. For example, sentence BERT, and extract the corresponding phrase embeddings. So after that, we utilize those embeddings to compute a cosine similarity, and we align the related phrases in a mutual selection approach. In other words, for every phrases in a premise, they are only aligned with the most related counterpart in the other sentence, that is the hypothesis. And for step two, phrase level NI prediction, we see that we already have some aligned phrases, and we concatenate each paired phrase embeddings and send those embeddings through a lightweight neural network, and are followed by a softmax layer to produce the phrase level NI probabilities for each individual phrase pair. And step three, since we already got the phrase level NI probability, we want to induce them into a final sentence level probabilities or final sentence level NI labels. And we do it through a fuzzy logic module. And we propose three different rules for each NI classes. So for the entailment, we expect that if two sentences are entailed, there should be every pair phrases. If every pair phrases is entailed, and we achieve this through mathematically through a geometric average. So for example, if there is one score in phrase level that is low, it can lead to the overall low sentence level score. And for the contradiction rule, if two sentences are contradictory, if there exists at least one paired contradictory phrase, and we will achieve this through a max operator. So it's just basically identify the strong contradiction signal from the phrases. So one strong contradictory signal leads to the overall sentence level contradiction score. And finally, for the neutral, if the two sentences are neutral, we expect there should be at least one paired neutral phrase and not any contradiction. And this aligns well with our human intuition. Finally, we normalize those scores after applying the fuzzy logic rules and let those scores add up to 1 so that we can compare those scores with the ground truth sentence level label, which is 1 hot, using the cross entropy loss, and to get the final sentence level NLI loss. And I want to mention that our pipeline or our EPR framework is trained with weak supervision, meaning that only sentence level NLI label are required during training. And after getting the loss here, or the sentence level loss here, thanks to the differentiability of our sentence level induction or the fuzzy logic, the gradient can backpropagate all the way to our phrasal NLI prediction and make the update to our phrasal predictors. And if we fit our EPR framework to our proposed symbolic bottleneck network, we see that the phrasal prediction module is actually our bottleneck. And when we train the pipeline with the input as the 2 tags and the output of the one sentence level NLI labels, we can expect that the phrasal reasoning in this bottleneck can emerge during training. So here's the evaluation process. We evaluate our EPR framework using the very widely adopted SNI dataset. And for the metric, we considered both the sentence level accuracy and the phrasal level performance. And since there's no phrase level labels available in the SNI dataset, so we do a human annotation and build a web interface. And we also propose 5 F1 scores in 5 categories to comprehensively to evaluate the phrasal reasoning of our EPR model. So let's take an example. If the human annotator think a kid in red should be entailed with the child in red, but unfortunately our model give the reasoning a kid in red should be entailing watching TV. So it's totally wrong, right? So and our metric can correctly give us the 0 F1 score. And for the main result, we see that our EPR model can achieve the state-of-the-art overall reasoning performance comparing with the some of the reasoning baseline. And it can also achieve competitive sentence level accuracy when comparing with the non-reasoning baseline. We've been also including some a large language model baseline as a reasoning baseline. By doing so, we consider the GPT-3 model, GPT-3 175 billion model, which was the best model at that time, and we provide our task definition with a 2-shot demonstration, and we see that.
Okay, so the contradiction is higher and all the other scores are lower.
Yeah, that's a good finding. Yeah. Yeah. Oh, sorry. Lee said he find that the contradiction score from the GPT-3 model is higher than ours. Yeah. Yeah, that's the finding. But the overall score is lower when comparing with our EPR model. And yeah, and for other than that, other than the performance perspective, we also see that there's some trade-off between when you're comparing with our EPR local model and the EPR concat model, where we concat the local and the global features, phrase feature for our EPR. You see that for the EPR local model, it has the highest phrasal reasoning performance. But for the EPR concat model, its sentence level performance is highest. But its phrase level reasoning performance is no better than the local model. So there's a clear trade-off between the two types of model. And there's also some very nice application of our EPR model. So our EPR model can be used to improve the NLI textual explanation generation, or the eSNLI task. So we feed the induced reasoning tuple from the training set and to the decoder model, and let the decoder model to generate the textual explanation. And we see that it can outperform all of our baseline. And here's a case study. For example, for the first three examples, A, B, and C, we show that EPR model can generate meaningful reasoning where its overall sentence level prediction match the ground truth label. So for example B, we see that a man playing fetch with two brown dogs is contradictory to the dogs are asleep. And by giving the reasoning playing and sleep is contradictory. And we also, to our surprise, we also find that EPR can allow us to identify incorrect label in the SNL dataset. And in example D, you see that this our EPR give a prediction of neutral, but the ground truth is interment. But it provides some meaningful reasoning, showing that black and white photo is neutral to the old photograph, and looking is neutral to admiring, which means that black and white photo does not necessarily imply the old photograph, which is meaningful. And to summarize our to summarize this study, we proposed an EPR framework that induce phrase level reasoning using neural-fuzzy logic under weak supervision, which means that at training only the sentence level label are provided, and this EPR can provide explicit intermediate reasoning step that can be inspect and validate. And finally, as an application, we show that our EPR-induced reasoning tuple can improve textual generation performance for the eSNLI task. So the broader impact of our EPR model is we think it bridged the neural and symbolic method. And we see that by pushing or putting the stricter rules in our bottleneck, we somewhat narrowing the bottleneck and make the pipeline more interpretable. However, it comes at the cost of lowering the overall performance, just like what we have seen in our EPR local model. And then finally, this also reminds us of the very old debate between connectionism, which is about a learner neural network, versus the symbolism, which is build a expert system that everything inside is symbolism. So let's shift our focus. Sorry. I can answer it if it is quick.
One objective could be getting the correct answer. Another objective could be matching what humans do. Humans are notoriously bad at certain types of inference. You know, Mr. Smith, Mr. Jones, and Mr. McGillicuddy own a horse, a cow, and trying to do the reasoning about that.
Yeah.
Are you expecting your tool to match the correct answer, or to match, you make confused where people get confused also?
I think
the puzzle mode.
I think I need more thinking of that. Maybe we can discuss later after the talk.
Okay.
Yeah.
Thank you.
Yeah, I think it depends on the training set. So if all your training labels are correct, then the model has the pressure to make a correct reasoning to get the final result. Yeah.
Okay, so let's shift our focus to the second part of this talk. We are going to talk about our research with the title, The Emergence of Trunking Structure with Hierarchical RNN. So in this, so I will first give you an introduction of the trunking test we are going to address in this study. So for the trunking task, it is about to trunk the sentence into meaningful phrases. So let's take an example, the cat ate deeply fried fish. There might be many ways to group those words into meaningful phrases. And one way might be the cat, we group the cat and ate deeply and fried fish. But this doesn't make any sense, right? Because we don't know what is the meaning of ate deeply. So a more meaningful way to group those words would be we just group deeply with fried fish together as a noun phrase and ate count itself as a verb phrase. So now this sentence make more sense in terms of both the syntax and semantics. So and this study is going to address unsupervised trunking, which means that we are going to build a model that can trunk the raw text without having the human annotated training set. And this is particularly helpful for the low resource languages. And in those languages, label parse tree are not even existed. And our unsupervised trunking can also verify some linguistic theory. So let's imagine if our trunking model can provide the syntactic structure like a noun phrase or verb phrase without being explicitly learned, it can show some evidence that those linguistic structures are not just manually defined. It somewhat emerged from our natural language or from the data. And finally, our unsupervised trunking can have a direct benefit for the downstream task. And let's recall that our EPR model still uses some heuristic to extract phrases as a reasoning unit. What if we can adopt our unsupervised trunking? We can expect that the meaningful reasoning unit can also emerge at the training time. So in this study, we propose a HRM model or hierarchical RNN model that to modeling the trunk representation. It is a lightweight two-layer RNN model that built on top of the transformer encoder model. And for the lower level RNN, it is to model the word-to-phrase composition. And for the upper level RNN, it is to model the phrase-to-sentence compositions. And this is a key part of our HRM model, which is we call the soft trunking gate. It is accomplished by a sigmoid function. So when its output is closer to 1, so it means that we should start a new trunk. If it is a value closer to 0, it means that we should continue the current trunk. So let's dive into how our trunking gate can handle both the cut and no cut situations. And here's for the cut situations, our lower level RNN hidden state is reset with the learnable HSOS tokens. But for the higher level RNN or upper level RNN hidden state, it takes in the lower level RNN hidden state with its own state to make an update. And for the no cut situation, our lower level RNN just act as the conventional word level RNN. But for the higher level RNN or upper level RNN, it doesn't do anything. It just keep idle at that point. And we unify both the cut and no cut situation by keeping our trunking gate or the M value a real value. So one of the main benefits of such design choice is now our HRM model is fully differentiable. It can be just directly applied on downstream tasks to learn in an end-to-end manner. And ideally, we just append or attach a decoder model after the HRM model and fine-tune the whole pipeline on downstream tasks directly. However, we find that this training from scratch often give us our HRM model noisy or trivial structures, which means that for the trivial structure, I mean that we find that HRM model may just cut every word as an individual phrase. So our solution is that we just break we just break the training into two processes. we firstly pre-train our HNN with meaningful initial structure by utilizing the trunking, the unsupervised parsing. And then we fine-tune the whole pipeline using the real downstream tasks such as summarization, translation, or like paraphrasing. And for pre-training HNN, our motivation of utilizing an unsupervised parser is because trunking is very closely related to parsing. And you can think of like a trunking as just a flattened form of parsing. And by utilizing the unsupervised parser, we can also keep our pre-training stage fully unsupervised. And this is the result of our pre-trained HRN. We see that our pre-trained HRN can outperform all of the unsupervised baseline. And it can also outperform the compound PCFG trunker, where it is used to provide the HRN model its initial trunking labels, which shows that our deep learning model or our HRN model can really smooth out the noise from the imperfect label from induced from our trunkers, initial trunkers. We also see that our HRN model can improve the transferability issues that we observed in our unsupervised method baseline.
Which was the issue?
You see that if you train the model on this Cornell dataset, it shows some good performance, but when you transfer it to the other downstream tasks, it is much lower. The trunking performance is much lower, but you didn't see these issues in our method. So for fine-tuning HRN, we just attach the decoder to the upper level RNN hidden state because it is the HRN provide us the trunk level representation. So now our HRN should be serious about trunk structure that be used in the decoder model for generating tags. And by training the pipeline on downstream tasks and optimizing on the downstream task, we can expect that meaningful trunking structure can emerge at training. And this is our result of the fine-tuned HRN model. We see that compared with the pre-trained model, our fine-tuned model can bring up further improvement by up to 6 percentage points. And we also see that our HRN model, when trained with the GigaWorld dataset or the summarization task, it shows the consistent best performance compared with the HRN fine-tuned with the other task or downstream tasks. And here's something interesting we found in our when we trained our HRN model. We see that there's an increase in the early stage of training, but after the training is going on, it decreases. But for the text generating performance, it consistently increases. Or in other words, when the model is good at generating text, it is bad at generating text at the early stage of training, it tends to create more human-like trunk. But after the training is going on, or its text generation performance is getting better, such linguistic feature or trunk structure is abundant, and the model prefers distributed features that are not that human interpretable. And we think this is very interesting, and we draw an analogy with human communications. Our human communicate in a low bandwidth channel, and we develop a linguistic structure in our natural language. This is similar to what we found in the early stage of training the HRN model, when the model is in a restricted channel. However, when the model is getting well trained, or the model is in a powerful channel, we find that our HRN model tend to abandon the linguistic feature and prefer a distributed feature that are not human interpretable. So let's imagine, so what if human can also have a powerful channel when we communicating with each other? And let's imagine that we can utilize our brainwave. By communicating with the brainwaves, we might not have a current linguistic structure as we know it in our current natural language. And let's take an example of what if we just communicating with our brainwave. We can just bypass the discrete concept like color and send the whole spectrum with each other directly. And we can expect that this information is more accurate. And here's a summary of our second part of the talk, or our paper, which is about the HRNN model. You see that our trunking structure is the bottleneck, or our HRNN model is the bottleneck for the whole text generating pipeline. And you will also see a trade-off just like our EPR model. We see that there's a trade-off between trunk level interpretability and the text generation performance when you take a closer look at this figure we show in our analysis. The line with the dash is the without pre-training. So it can generating higher text generation performance, but the trunking is bad. For summarization, we consider the Rouge score, and for the trunking task, we consider two metric, which is the phrasal F1 and the accuracy, based on ground truth. Yeah. So let's end this talk with a discussion and the future directions. So I would like to give a discussion for comparing our bottleneck method and the fully end-to-end method. So the pros of our approach is, or the bottleneck method is, it encourages explicit intermediate representation, but it comes at the cost of sacrificing model capacity and the performance. But on the other hand, for the fully end-to-end neural network, it is more capable, it's more flexible, and it can lead to higher performance. But the major drawback of this end-to-end neural network, it lacks explicit intermediate reasoning steps. And another different perspective of reasoning before giving the final answer is chain of thought. It is particularly used in the large language model domain. So in chain of thought, or COT, the end-to-end large language model generates free form, but natural language before giving the final answer. And they show that by working on chain of thought, they can improve the reasoning performance of a model. And when comparing this chain of thought with our symbolic bottleneck, we find that the difference is the chain of thought reasoning is in the output level reasoning, where the reasoning step might not perfectly mirror the model's true inner logic for the output. This is in contrast with our symbolic bottleneck. And this is a previous paper showing that the output level reasoning, or the chain of thought reasoning, is not always faithful. For example, it might hallucinate when giving the final answer, although they have a perfect and a nice reasoning step. And for the future direction, one direction might be we can bottlenecking our chain of thought reasoning to improve the faithfulness. And this is the end of this presentation. Thanks for your time.